This is GCSE Chemistry Higher Tier Paper 1, 2023. This is for the exam board AQA, and let's start with question 1. Atoms were originally thought to be tiny spheres that could not be divided. The plum pudding model of the atom was then developed. Figure 1 represents the plum pudding model of the atom. Describe the plum pudding model of the atom. Okay, let's equip the draw tool. Yeah. Well, we know that the plum pudding model of the atom is a sphere, essentially a ball. So we'll just say that it's a ball of positive charge as that's what this plus is for. And then we have these negative electrons embedded within the atom too in this model. So our second point would be negative electrons embedded in the positive ball of charge. 2 marks. 1.2. Atoms contain electrons, neutrons, and protons. Write these 3 particles in order of their discovery. The earliest would be the electrons. I think they were discovered before the 1900s even began. And next were the protons. They were the 1920s, I believe. And of course, you had the neutrons in 1932. Next question, 1.3. So we have the element tennessine, and its atomic number is 117. We have to predict the number of outer shell electrons in an atom of tennessine. Give 1 reason for your answer. Use the periodic table, so you have to use the insert. Looking at the insert, we can see that 117 is over here in the bottom right. If we zoom in further, we can see the tennessine, yep, tennessine 117, and it belongs in group 7, the halogens. So we can say that there will be 7 outer shell electrons in the group of the halogens where tennessine belongs. The reason is, I'm just going to write it is in group 7, the halogens. Question 1.4, we have tennessine being first identified by a small group of scientists in 2010, very recently. It's just one reason why tennessine was not accepted as a new element by other scientists until 5 years later, 2015. Well, scientists always need to peer review each other's works, so I think the primary reason here would just be peer review time needed. As you can see, it took 5 whole years from 2010 to 2015 to thoroughly peer review it. Question 1.5. Element R has 2 isotopes. Table 1 shows the mass numbers and percentage abundances of the isotopes of the element R. We have mass numbers 6 and 7 and percentage abundance 7.6 and 92.4 respectively. Calculate the relative atomic mass AR of element R to 1 decimal place. Well, AR is just simply going to be the mass numbers multiplied by the percentage abundances, the sum of that divided by 100. So we have 6 times 7.6 plus 7 times 92.4 all over 100. And our AR value will come out as, after we throw it into our calculator, bear with me a minute, 7 times 92.4, that's the sum, divided by 100, Okay guys, we have a number of 6.924, but since it's to one decimal place, it will just be 6.9. Next question, we're on question 2. This is about temperature changes. So a student is running an investigation to investigate the change in temperature of a solution. This might be important when different masses of ammonium nitrate were dissolved in water. So they measured 200 centimeter cube of water and put it into a polystyrene cup, measured temperature of water, add 4 grams of ammonium nitrate, and then stir the solution until all the ammonium nitrate has dissolved. Measure the lowest temperature reached by the solution, and they simply just repeat the steps. Give the independent variable and dependent variable of the investigation. Independent is what will change throughout the investigation. So throughout the investigation, we can see that each time the student will use different masses of ammonium nitrate. Keyword here being different. That indicates the change in masses that the student will use each time they run the investigation. So we'll just write mass of ammonium nitrate. The dependent variable will be whatever we're measuring. And this question is about temperature changes, and the student investigates, well, temperature. So our dependent variable is temperature when we're going to be measuring temperature. Specifically, the lowest temperature reached by the solution. Next question, we have table 2, and we need to plot the data from table 2 on figure 2. Draw a line of best fit. Well, my line of best fit is going to be wonky, but you guys have to draw a good line of best fit because you guys have access to a ruler. So let's start plotting. 4 grams, 8 grams, 12 grams, 16. So the mass seems to be going up in 4 along this axis. That goes along in 5. And we have a lowest temperature ranging from 10.6 to 18.2. So let's go from 4 to 18.2. Okay, 10 boxes between each interval. Divided by 10. Each small box is going to be 0.5. So this is going to be 4 over here. And we're going to have 4 and 18.2. There are 10 boxes between these two intervals, and then the value of the interval is 2. So 2 divided by 10, each little box is going to be 0.2. So for 18.2, it would be marked here. (8) and 16.2. (8) would be marked here, just in front of 7.5, and the value is 16.2, so it'll just be another mark here. 12 and 15.2. So going along to 12. 12 is going to be 4 small boxes across, so here's going to be 12 behind 12.5, and the value for 12 was 15.2, and 15.2 is going to be around here. Then we have 16, 13.6, 20, 12.4. So 16 is here, 13.6 would be, this is 13, 13.6 is going to be 3 up, so it's still going to be there. we have 20, 12.4, 24, 10.6. So 20, 12.4 can be right there. And 24, 10.6 is going to be right here. 10.6, so it's going to be there, roughly. Drawing a line of best fit. You know what, we'll take that. And the line of best fit seems to reach this y-axis up here, which is crucial for the next question, as they want us to determine the initial temperature of the water. So the initial temperature of the water would mean that there will be no mass, zero mass of ammonium nitrate added. So looking afterward, when we extrapolate to the y-axis, we get a value over here. And this value seems to read 19.4 degrees C. So I'll write that down. How did the results show that the dissolving ammonium nitrate in water is endothermic? Well, the key point about endothermic reactions is that we see a temperature decrease. So temperature decreases. (2.5) Explain why the student included plus minus 0.3 degrees C after the meanest to lowest temperature. Whenever you see this sort of tolerance symbol, plus minus, you know that's an uncertainty. So there is a 0.3 degrees C uncertainty involved, which to get your second mark, you need to explain what we mean by uncertainty. And what we mean by it is that there is a range of 0.3 degrees C around the mean lowest temperature. About the mean lowest temperature. And that will give you your second mark. Cool. Next question. What type of error is shown by the results in table 3? Well, they all seem very close, so it's not going to be a problem with the method, so it's not a systematic error, and therefore by default it's not going to be a zero error, because zero errors are often used on often involve apparatus like measuring balances. We'll just draw one real quick. So this is the measuring balance. Say there's something on it, but it reads 0. Or so basically, if you misuse this technique, or if you forget to zero it before adding something else to weigh by difference, then that's essentially called a zero error. So it's got to be a random error here. This question 3. This question is about making a soluble salt. Plan a method to make pure dry crystals of zinc chloride from zinc carbonate and dilute acid. Well, we need a beaker, so we'll add both the reactants. We'll add the zinc chloride and zinc carbonate together. That's going to be your first bullet point. Mention a beaker, adding them into a beaker, and you can stir it. We have to add the zinc carbonate in excess, and the way we can identify the zinc carbonate in excess is when there is excess solid present, or precipitate, the scientific term, or effervescence, in this case CO2, because it's a carbonate. So CO2 bracket, so I'm going to put that in brackets, we just write effervescence when effervescence is no longer present. Or just simply stops. That's when you know you've got you've reacted one of your reagents in excess. In this case, we need to react zinc carbonate in excess, because zinc carbonate is where we will get our zinc from, and our chloride is most likely going to be from our dilute acid, in this case probably dilute HCl. So we've gone through the reaction phase here. Now we have to remove the solid / precipitate. So for our filtration phase, we will just use filter paper and a filter funnel to remove the excess zinc carbonate. And the precipitate in general. So now we've gone through the filtration phase, and now we need to go to the crystallization phase. So we can pour the solution into an evaporating basin, or we can heat the solution, which is probably a better way to guarantee a mark. Heat a solution, heat the solution, the remaining solution after you filter, with an electric heater, or you can use a warm water bath. It's up to you. You can write either point down, and then lastly, for the crystallization phase, you can just leave it to crystallize. There you go. 3.2. Name 2 other substances that can be reacted with dilute acid to make zinc chloride. Do not refer to zinc carbonate in your answer. So we just need to find another zinc salt. The most common types of salts you have are oxides and hydroxides. So I'm just imagining probably zinc oxide and zinc hydroxide as your 2 other potential reagents that you can use. Question 4. It seems to be on bond enthalpy, bond energies. And we have some displayed formula here in figure 3. Which expression shows how to calculate the overall energy change for the reaction in figure 3? Well, for the reaction in figure 3, since we're considering bond energies, it's going to be the sum of the reactants minus the sum of the products. So we'll probably take this 436, add it to this 346 to make up the sum of the reactants, and we'll subtract it from the sum of the products, and we have two HCl bonds. So we're going to take away 432 times 2. Looking down here, it's going to be this last one. Yep, there we go. Took me a second to see, but yeah. Next question. Explain why this reaction releases energy to the surroundings. The reaction between hydrogen and chlorine is exothermic. Well, we know that bond breaking, so bond breaking requires energy. Bond breaking needs, I'm going to just write E for energy. No, let's not be lazy today. Let's write energy fully. Bond breaking needs energy. And bond forming, don't forget the word and. I'm going to put the symbol here for and. But putting and there is key. And bond forming releases energy. So when it considers an exothermic reaction, that essentially means that more energy is released than needed to break the bonds. More energy released than needed to break bonds. And here's going to be your first point, establishing with which either of the two, bond breaking or bond forming, needs energy or releases energy. And your second point, second mark, is just going to be stating, just going to be addressing the question, what is meant by an exothermic reaction? And that's when more energy is released than needed to break bonds. 4.3, we have a graph, a reaction profile. You should label the activation energy and label the overall energy change. The activation energy is the minimum amount of energy needed for a reaction to occur. It's just a standard definition that you need to know. So for a reaction between hydrogen and chlorine, we established that it would be exothermic, as we see up here. So the products are going to end up somewhere around here, and it's going to be 2HCl. Probably don't need to write that, but we will anyways. To complete the reaction profile, again a wonky line, not the best curve, but it will do. And this is going to be this gap between the reactants and the peak, that's going to be your activation energy. Just going to EA symbol, activation energy. But your overall energy change is going to be from the difference between your reactants and products. So going from up to bottom, up and down. This is going to be overall energy change, also known as delta H in some cases. And 3 marks, yeah. So I think you'll get 1 mark for labeling activation energy, another one for overall energy change, and maybe 1 for whatever the product is, which we know is going to be HCl. And draw a dot and cross diagram for a molecule of hydrogen chloride. Show the outer shell electrons only, so HCl again. Hydrogen chloride, okay, cool. Take a hydrogen, we know it will only have 1 electron, let's call it a circle, because dots versus crosses. And we know chlorines are halogens, group 7, they will have 7 electrons around them. So they have 1 pair here, another pair here, another pair here, and they'll have 1 left over, but they'll be sharing it with the hydrogen. And there we go, here's your dot and cross diagram. We have a covalent bond in the middle, and we have all the other lone pairs surrounding the chlorine. Question 4.5. Methane versus polyethylene. Methane is a gas at room temperature, but polyethylene is a solid at room temperature. Explain why methane and polyethylene exist in different states at room temperature. So we can go about it 2 ways. We can talk about how small methane is compared to polyethylene, or how big polyethylene is compared to methane. I'm just going to pick methane because the question mentions methane first. So I'm going to be addressing it that way. We're going to say methane is made up of smaller molecules, and between these smaller molecules there will be weaker intermolecular forces. I'm going to just call the IMF for intermolecular forces, but in the exam you should refer to it fully. Weaker intermolecular forces between molecules, and therefore they'll need less energy to break, and so methane will have a lower boiling point or melting point than polyethylene. To break or overcome, I guess you can use something along those lines. And lower BPT or MPT, boiling point / melting point. There's your 4 marks. First one is mentioning the difference between molecules, and then the second one is talking about intermolecular forces. Third one is talking about the energy needed, difference in energy needed to overcome them, and the 4th mark is just give a final statement that methane has a lower boiling point, melting point, than polyethylene, or if you went down the other route, polyethylene has a higher boiling point / melting point. Question 5. Question about acids and alkalis. Ethanoic acid is weak acid. What is meant by a weak acid? Just in terms of ionization. So usually you can use the words dissociation here, but since it's about ionization, we can't use the words dissociation. So we'll write down instead, we'll just directly substitute two words, and we'll say that a weak acid is an acid that partially ionizes, or is partially ionized in aqueous solution. AQ solution. Next question. The concentration of acid can be can be measured in moles per decimeter cubed, which combination of changes increases the concentration of acid. So here we're just looking for more moles and a smaller volume. And since moles is mass over mR, to get a higher mole, we need a higher mass, as they will be directly proportional. So looking at the first one, mass of acid dissolved in half, solution is half, no, it can't be that one. Mass of acid dissolved in half and volume is double, no, that's just diluting it, not increasing its concentration, it's decreasing its concentration. Mass of acid dissolved, doubled, volume solution is half, nope. Wait, did I read that wrong? Mass of acid dissolved is doubled. Yes, the mass goes up, we need that, and the volume of the solution is half. Oh yeah, we needed that too, because we said volume should go down. So yeah, it's going to be the third one, but I might be messing up, so I'm going to read the last one, see what it says. Mass of acid is also doubled. Yep, we need that. Volume of solution doubled. No, we don't need that. We need a smaller volume. So it's going to be the third box actually. Double the mass, half the volume. 5.3. An indicator is added to an alkali in a flask. Name an indicator that can be used in this titration. Right. I tend to just always go with phenolphthalein. Very difficult to spell. I don't even know if I spelled it correctly here, but we move. Color change from pink to colorless, I believe, when it becomes more acidic, when something becomes more acidic. And since we're adding an acid, yeah, we're adding an acid from urate. Yeah, pink. It'll change from pink to colorless, I believe. It's just one of those things that you have to remember. Sodium carbonate dissolves in water to produce an alkaline solution. Give the formula for the ion that makes the solution alkaline, so H minus. And if this question asked for what ion makes it acidic, it will be H plus. 5.5, a titration calculation question. Oh, they've given us the steps here. So all we have to do is follow these steps and always answer to 3 sig figs. And the question is actually to calculate concentration of the nitric acid. Cool. This is going to be a nitric acid, and we find the concentration. So our first step we have to do is find the number of moles of sodium carbonate in 25 centimeter cube of solution. We're given both the concentration and volume. So to find moles, we'll have to convert this volume into dm cubed by dividing by 1,000. So 25 over 1,000 times by 0.124. Plugging that into our calculator. One sec, guys. And I'm getting 3.1 times 10 to the minus 3 moles of sodium carbonate solution. So we got 3.1 times 10 to the minus 3 of this, and we need to find this. It's a 1 to 2 molar ratio, so the HNO3 is going to have double the moles. So if we double this value of 3.1 times 10 to the minus 3, we will get 6.2 times 10 to the minus 3 moles of HNO3. I'll give you your second mark probably. And we need to find the moles of nitric acid in 23.6 centimeter cube of the nitric acid. Cool. We're given volume of the nitric acid. So once again, we've got to convert that volume. And to find the concentration, it will just be moles divided by volume. We have the moles. So let's convert the volume first. 23.6 divided by 1000 to get into decimeter cube. And since we have to do moles divided by volume, we have to divide it by n. In this case, n is 6.2 times 10 to the minus 3. So putting that into a calculator, 6.2 times 10 to the minus 3 divided by 23.6 over 1000, get 0.2627118 6, and since it's the 3 sig figs, we have to cut off the line here at 0.627, so round up the 2 to a 3, should get 0.263 moles per decimeter cube. So you get 1 mark for finding number of moles. You'll get 1 mark here for your second mark for doubling, seeing this molar ratio 1 to 2. Third mark would be to divide again, convert the units over here. Fourth mark, divide the moles by the new volume. And your final mark is to just round to 3 sig figs. 5.6. What is the concentration of H+ ions in a solution of hydrochloric acid when the pH is 2.5? So we're given a pH of 4.5, and this is the concentration. Changes in pH follow a base 10 order. So what do I mean by base 10 order? The lower the pH, so we have 4.5 and 2.5, we can see that there is a difference of 2. Therefore, there is a 10 to the 2 difference. Since it follows base 10, if there was only a difference in 1, it would just be a 10 to the 1 difference. But here it's a 10 to the 2 difference. So essentially we have a 10 to the minus 5 times 10 squared to get 10 to the minus 3. The number in front just stays the same, and we know that it's now to the minus 3. 3.16 times 10 to the minus 3 for a pH of 2.5. 5.7. Which element has atoms that have the same electronic structure as the chloride ion? Use the periodic table. I think this is the last question for part 1 of this video. And using the periodic table, we have to go back to the insert. For a chloride ion, it will be Cl-, it will have to gain an extra electron. So instead of 17, it will have 18 electrons. And as we can see, one across from chlorine, what has 18 electrons? An argon atom. So that's our answer there. Argon. And this brings about a close to part 1 of this paper. Thank you for watching the video. This is a bit longer. I'll keep the next video shorter for you guys. And have a great day. Goodbye.